Hey, looks like we're starting our class here. I have Brian here. Brian, can you hear me? Or if I need to change that camera angle. Hey, Brian, can you hear me? Not too crazy about that camera angle. Hey, I think we've got somebody. Hey, there's Ben. There's another person. Let's see who we got here. We got Ben and Brian. Anybody else? I'm not too pleased with this. Hey, that's more like it. That's doable. Hey, well, there's Ben. Hey there, Ben. Hey, good to see you. Yeah, now this is better. Now, Ben and Brian, I was under the impression this class starts at 9:30. Is that what you think too?
That's what I saw.
That's what I thought too. I'm trying to get this camera to, yeah, maybe that's not too bad. I've got this new camera here. It's being a little bit ornery. Yeah, but that's not too bad. You guys can see that. I wish I could get rid of this picture of me over here. I don't want that stinking picture of me. Let's see if I can get rid of it. Yeah, that helps a little bit. And that camera slipped on me. Doggone it. So we'll just try to change the angle on that. It doesn't change. Let me turn this other light on. Need all the light I can get here. Okay, well, let's see how far down this goes. This goes down to here. I want the whole page on there. How do I get that? Maybe like that. Now, how far can I go down to there? Okay, I just can't right below that. Well, all right. Well, let's see who we've got right now. We got Ben and Brian, and that's it, just the three of us. I hope there hasn't been a foul up. We're in strength of materials. And what I want to know from you two guys is, were you able to pull up my syllabus and my schedule on Blackboard? Were you?
Yes, sir.
Yeah, I was able to do that.
Good. Both of them?
Yes, sir.
Good. Looking at the calendar, And I wrote down some stuff about the calendar, but where did I put that? Now, here it is. September 7th is a holiday. It's Labor Day. So I don't know if that affects us any. Let me look at September here. Nah, that doesn't affect us. That's a Monday. Forget it. Then November 6th is the last day to withdraw or get an audit. Here, I'll write some of this. September 7th. That's a Monday. So if you have a class on Monday, forget it. There won't be any. And then November 6th is the last day to withdraw, student withdrawal, or switch to an audit. But you guys aren't going to do that. You're going to stick with me. Thanksgiving is November 25th through 29th. And finals are December 7th through 13th. You could look all that up in the calendar there under Blackboard. You didn't need me to do that. I just wanted to write some stuff on the board. Okay, well, great. Well, so what? Well, I guess we could look at the syllabus a second. Let me see if there's anything important on that. I've got a copy here of the syllabus someplace. Yeah, here it is. The book. Ta-da! That's the book, guys. It's by a guy named Hibbler. It's the 10th edition. It tells about that in the syllabus. Let's see what it says. It says, I'm looking at the syllabus here. It's on Blackboard. And it says, oh gee, this is the blank. This is the blank syllabus. I need the actual syllabus. Just a minute. Okay, I think this is the real thing. No, that's another blank. All these are blank. I guess you're going to have to look it up on your Blackboard. But I'll tell you what it'll say. It'll say that this is the book. It's Mechanics of Materials. It's by Hibbler, Hibbler. I don't know if you can read that. It's the 10th edition. The publisher is Pearson. Here, let me write some of that down for you. Mechanics of Materials. The author is Hibbler. The publisher is Pearson. And it's the 10th edition. You can get that book through the bookstore, TCC bookstore. You can get it through the publisher, Pearson. I bet you could get it through Amazon or Barnes and Noble. And if I remember right, there's some places that will offer it as a rental. You can rent the book. It's real cheap. I forget how much it is, but it's just a thought. You could save money. You might be able to get the book also as a electronic book. That'll save you some money. So whether you get a new book or a used book or an electronic book or whether you rent the book, that's the book. I think on the syllabus, it even has the ISBN number. I could give it to you, but if it's on the syllabus, you don't need it. I asked what that stood for, and somebody said it's the International Book Number. Book BN is book number. International. I think it's International Standard Book Number. I believe is what that stands for. So that's the book. The syllabus tells you what the homework is, when it's due, and how to do the homework. And then the schedule tells you when the tests are and what homework is due. And read them. Read the syllabus. Let's just write it down here. Read the syllabus. And read the schedule. Okay. Any questions so far? Well, according to the schedule, we're supposed to study, I think it's chapter 1. So let's start studying it. And it says on the schedule that today on the 18th, we do a statics review. So here, let's do a statics review. Here we go. Again, any last comments or questions before we start a statics review? Let me see who's on board here. Oh, we've got a good crowd. Look at this. We've got Alex and Nicholas, Julian, and Darren, Ben. I think some more here too. Let's see who else we have here. I don't know how to, there we go. We have Shane and Noah, Mohammed and Megan and Jackson and Hal. I remember some of you guys because I've had you before. And Damon and Brian, we got a great group. Okay, any last comments or questions before we have a statics review? Now wait a minute, do I have everybody muted or what? Let me see. Maybe I've got everybody muted. I don't know. It says unmute all, so I'll do that for right now. You're all unmuted. Anybody have anything to say? Anything to say?
Good morning.
Hey, good morning. I heard that.
How are you?
I'm fine, thank you. Yeah.
Good
Beautiful
to be back
day.
in class.
I didn't quite hear that last one.
It's just good to be back in class.
Yeah, isn't it great? It's good to be back. My audio is kind of weak. Do you suppose there's a way I could turn up my volume? I don't know how to do that. Oh, well, I can hear you. Okay, statics review. Here we go. All right, now I scribbled down some things here. When you solve a problem in this class, you have to decide on what your body is or your system. You have to know what is part of the system you're studying and what isn't, and you don't want to get mixed up. And then you want to make a sketch. You want to do a free body diagram, we call it. It's a free body diagram, and you want to, let me write that out for you. They've called it that for years. It's kind of a weird name. But we'll do some free body diagrams, and then see what you do with that as you put your forces in there. Get yourself a red pencil or pen and put your forces in red. Does that come out red on the, yeah, it kind of does. Put your forces in red. And where students can get mixed up is they'll put forces in, but they're not on the body. They're on maybe something else outside the body. That's why you have to decide what your body is. And when you do this, you want to do it to scale. And you want to measure your angles. Measure stuff. See, get yourself a ruler. Ta-da! Get yourself a ruler so you can measure stuff. This has got metric and English. Get yourself a protractor. Ta-da! I got a protractor here. Measure your angles. Measure and do everything to scale. Okay. And then the next thing you do is you look for 0, 2, and 3/4 members. Maybe we can show you some examples of that later. 2-force members come in 2 types. There's tension and compression. Here, I'll draw you for, if you have a tension member, I like my forces in red. Well, then it's being stretched. See, you have your forces going like this. That's a 2-force member. It's only got 2 forces on it. Now, if it's a compression member, then the forces are pushing like that. That's the 2 types of 2-force members. Tension and compression. Hopefully I'm boring you because you already know all this stuff. This is compression. Now, if you have a 0-force member, we'll show you one of those sometime. 3-force members. Now 3-force members come in 2 types. There's concurrent. 3-force members are either concurrent or they're parallel. Now, is that showing up on our screen? Yeah, that's showing up pretty good. 3-force members are either concurrent or parallel. Concurrent means that all of the forces go through a point. Parallel means that all the forces are parallel. We'll show you an example of that. Okay, step number 4. I'm running out of space here. Step number 4 is you solve for all the external forces. Solve for all the external forces. and moments. You might have moments. That's possible. Solve for them. And then step number 5, if they want you to find internal forces and moments, then you have to break. Oh, by the way you solve these is you use these equations right here. This is how you solve for the external forces and moments on your whole system now. We're just dealing with the whole system. Well, I ran out of space, so I'm going to have to go to number 5 now. But here's a nice little checklist. Let's go to number 5 now. Number 5. If they want you to find the internal forces and moments, we can call them internal loads. You could call these external loads. But to find the internal loads, you have to make sections. Uh-oh, ran out of room here. You're going to have to section this. And there's 3 ways to section a system. You can make pins. You can talk about pins. Or you can talk about members. Pins, members, or sections, where you maybe cut the whole system in half or thirds or whatever. And then once you decide on whether you're using pins, members, or sections, then guess what? To solve, you have to use these equations again. But you're going to use them this time on your chosen pins, members, or sections. You're going to do it on your parts. Let's just say on the parts. You have, instead of saying make a section, you have to break it into parts. Break it into parts. If you want to find what's going on inside, if you want to find the internal loads, you have to break it into parts. And then guess what you do after that? Well, I skipped something. Really, before you do that, you should do this. You should look for 0, 2, and 3/4 members on your parts that you broke it into. Then you solve for the forces that are acting and the moments that are acting on your parts. Okay, and then finally, when you get all through with all that, the last step, I guess I need some room here. I think we had step 5 there, maybe. The last step is you want to check your work. Now, there's several ways to do that, and I'll try to show you, and maybe you can remember how to do that. One way is get a buddy and work with a friend, and the 2 of you together, that you can find each other's mistakes that way. It's hard to find your own mistakes. In other ways, you can look in the answer book if you're lucky enough to have an answer book. Another way of checking your work is to look at the units. The units have to work. Check your work, check your answers, check your units. There. Now we've just given you a statics review. Do you have any questions on the statics review? Well,
Get
let me
back
go
over
to
zero.
go ahead.
Get back over zero force members.
Yeah, okay, I'll do a zero force member for you. Thank you for asking. Let me make a little room here. Suppose you had a truss. And who am I talking to? Who asked me this question? Who is it?
Jackson Wilson.
Oh, Jackson. Good going, Jackson. Thank you for asking. Jackson wants to know if you had a truss like that. Now you need some kind of external load. Why don't we put an external load right here, Jackson? There we go. Now you know there's got to be some external loading going on here. It kind of depends on the angles. I didn't draw those exactly equal, but it turns out, Jackson, that this member right in here is a zero force member. Now the reason why it is this is a truss, and trusses are composed entirely of two force members. That's what a truss is. It's a structure composed entirely. Let me write that. A truss is composed entirely or only of two force members. It's just that this one here, I don't know what to call it. Let's say this is A, B, C, D. BD is a two force member, but both forces are zero. You got zero, I don't know, kips maybe, and zero kips. It's not tension or compression. It's a two force member. It's just that both members are zero. By the way, a kip is 1,000 pounds. I hope you know that. But if you don't, I'm glad you're tuned in, because that's what a kip is. It's a kilo pound. A kip is a kilo pound. Now here's the reason why. Do you see this pin D right here? This is pin D. We are looking at pin D. Well, it turns out that these bottom members are tension members. And so it has a tension member that's pulling on it, AD. There's AD. And it has a tension member, DC, pulling on it. And the other, they have to be equal. They have to be equal because that pin can't go anyplace. Now, if this is a tension member, then that would be pulling on it. But see, you can't have just one force on that pin or it would move. In statics, nothing moves. That's what the word static means. It doesn't move. So there is no other force going down. I don't see any force going down here, do you? And so that force has to be zero. That force has to be zero. And these forces here, these are not zero force members, but BD is a zero force member. Here, let me draw it for you. There's more room over here. Here's BD. Now we know that there's no force down here at D. Zero force at D. So you can't have a force at B, I'm sorry. There's only two forces, and if that one's zero, then that one there has to be zero. Now there's forces all right in these members here. They're compressive forces. Jackson, did I explain that where you understand it?
Yeah.
Are you saying yes just to be nice, or do you really understand it?
Yeah, it's just been a while since I was last in statics, so.
Good. Well,
Interview a little bit.
thank you for asking. Now let's see, where was I? Oh yeah, I want to do a problem now. I want to do a problem to illustrate. And you're going to have some homework. Let me tell you what your homework is. It's on Blackboard, and you can pull it up. But well, let's make sure you understand. There's some homework, and it looks like, gee, it's not much. See, I'm a real easygoing guy. F12. It happens to be on page 16. That's all the homework, and it's not due till the 21st. What is that? Is that Friday? Let's see, today's the 18th, 19, 20, 21st. Tuesday, Wednesday, yeah, Friday. Friday at midnight, guys, you think you can cut it? I know you can. Okay, now the problem we're going to do together right now, I'm totally organized here, is it's on page 16. That's your homework. Well, this is on page 16 also. Let me find it here. Okay, this is F 1-6. Okay, we're going to do this problem. That's your homework. Let me erase that. It's on Blackboard, but this is not on your homework. This is just for fun for us to do, to practice doing statics. And remember, I gave you step by step how to do statics problems. And the first thing you got to do is write your free body diagram to scale. So let me get my ruler out. And I need to have a 3, 4, 5 triangle here. I wonder if I could do inches. I don't see why not. Let's have inches. Yeah, guys, wouldn't it be better to have a scale of 8 inches though? Yeah, that's what we'll do. So we'll have that 8, and this will be 3. Well, that'd be 6. Yeah, there we go. Yeah, we're doing this to scale. And then we got this here. Let me make some room here. This is problem F 1-6 in your book. And how long is this thing? Well, it's 6. So that'd really be 12, wouldn't it? Man, I don't know. I don't know if I got enough room for all this. Yeah, we'll make it. I'm trying to do this to scale. How far is it now? It should be 8. Yeah. There we go. Yeah. All right, well, here, let me draw this thing here. I've tried to draw this thing to scale. This way I know how. And there's a distributed load on it. Yeah, now how big is this distributed load is the question. Well, sorry, it's messy there. Yeah, it's 5 kilonewtons per meter. Okay, and now this, did I make that 8? Yes, did I make that 8? Yeah, pretty good. Pretty good. Yeah, let's try to draw this thing. It's a bent rod, you know it? It's a bent rod. Yeah, there we go. This is 4 meters, 3 meters, and that's 6 meters across the top. So that makes that 4 meters, that makes that 2 meters, doesn't it? Should be 4 inches on my scale. Wait a minute, I think I goofed up. If that's 4 meters, this should be 8. 4 meters 8. This should be 6. Yeah, and this should be well, it's supposed to be 12, right? Yeah, yeah. I made this too big. That's okay. This should be 4, and it is. Now you're supposed to do your homework. If you'll read the syllabus, you're supposed to do your homework on engineering paper. And if you have engineering paper, it has a graph, a grid, and you can make these angles right, and you can measure these and get them to scale. Look, I did this to scale. See, this is 4 meters, and this is 2 meters. I did it to scale, didn't I? Okay, let's label all this stuff. This is A. Now, they want us, for some reason, to label a place in here called C. All right, we'll do that. And this is B. There's B. And this is D. There, we labeled all that stuff. Now, what do they want to know? They want to know the internal forces at C. You guys need to understand that there's external forces and there are internal forces. And when we study stress, stress is always based on the internal forces. And we'll find the stress. Do they want to find the stress? No. All they want to find is the forces. But we'll soon be talking about stress. You see, there's normal stress. And what that is normal force over area. And there's shear stress, which is shear force over area. But normal force and shear force are internal forces. Okay, well, now our first job though is to figure out all the external forces. Okay, well, here goes. We are going to write this distributed load. What is it? 6 meters? 6 times 5 is 30. So we're going to put that right in the middle. Well, what's the middle of the very middle, according to my scale, would be right here. And this is the resultant force of that distributed load. And it's 6 times 5, it's 30 kilonewtons. That's your external force there. And we need to find out what the forces are at A and D. That's what we need to find out. We don't know what they are. But it did say to look for 0, 2, and 3 force members. Do you ever wonder why we don't look for 1 force members? Because you can't have a 1 force member in statics. Now, our course is called Strength of Materials, but it's still statics. If you have a body with only 1 force on it, that body is going to move. And it's not going to be in our course. We're still in statics, really. But it turns out that this crooked member BD is a 2-force member. It may not look like a 2-force member, but I'll tell you what, it's only got a smooth pin at D and a smooth pin at B. So it's going to have a force that does this. Because remember, there's only 2 kinds of 2-force members, compression and tension. And this one's going to be compression. I should make that red, though. I like my forces in red. Hey, we just found out the direction of this force at D. Let's call it D, would be a nice name for it. Okay, great. Now, if you drew this bent member here, there would be a force, compressive force on it in line with that force at D. Now let's look at A. Well, can you tell that at A, it's got to have a force going to the left, because this has a force going to the right, but it also might have a vertical force. I don't know. We don't know yet. It might have a force going up. We don't know. We don't know the amount of this force D or either of those forces at A. We could give them names. We could call this AX, and we could call that AY. That'd be okay. If anybody just tuned in, what we're doing is we're reviewing some statics. We're doing problem F16. It's on page 16 in your book. And we've tried to draw the free body diagram to scale. You're supposed to do it on engineering paper. And the syllabus says to write out the problem exactly as it's expressed in the book. They say, determine the resultant internal normal force, shear force, and bending moment at point C in the beam. Well, we'll do that. And we'll follow the step-by-step methods of statics that I tried to show you earlier. And we will put this on YouTube. You could watch this over again if you didn't get it the first time. But now how do you find these external forces? Well, according to our step-by-step method, you use these equations. You go the sum of the forces and the sum of the moments. Well, let's do the sum of the moments, and you have to pick a point. Always pick the point where you know the least. I don't know what either of those are, so I'm just going to say the sum of the moments about point A is going to be, well, it's going to be 30, well, it's a negative 30 kilonewtons times, I'm going to have to think about this. I think it's 6 meters from here to here. See, it's 4 meters from here to here, but no, wait a minute. No, that would be 3 meters, wouldn't it? Yeah. See, on my scale, that's 6 inches, so that's 3 meters. Okay, and then you have a positive. Well, that has components is the problem. Here, let me draw the components. At D, you have a dy going up and a dx. That's the component in the x going to the right. So you have a positive dx times this 3 meters. And that's equal to 0 because the sum of the moments has to be 0 in statics. I want to know how come that's a minus though. Let me ask one of my wonderful students here, see if they know. We have a lot of wonderful students here, and I'm going to pick on Shane. If you can unmute Shane and tell me how come this moment here, this 30 kilonewtons going down at 3 meters across is negative. Shane, how come that's negative? Unmute. Shane's not going to tell me. Here, I'm going to unmute all. Somebody tell me, how come that's negative?
Because it's
That's
in
kind
a
of why it's going
Clockwise
up.
direction.
Positive.
Because of what?
it's going clockwise in relation to the
That's the
point.
answer.
Clockwise.
It's clockwise. See, about this point O,
Oh,
this would make you spin clockwise. Clockwise is negative. Clockwise is negative. Counterclockwise is positive. That's how come this one's positive. Because see, this dx tries to spin you counterclockwise about point A.
I actually have a question about that second member.
Yeah, go ahead.
Why is it dx instead of dy?
Well, dx is, the x direction is this way,
Yeah,
and the y direction is this way. And what I'm saying, tell me your name.
Darren.
Darren. What I'm saying, Darren, is that this force D here has an x component going to the right,
Mm-hmm.
a y component going up. And what is your question, Darren? I didn't understand the question.
Why is it the x component of the force at D instead of the y component of the force at D?
Oh, thank you for asking, Darren. This y component goes through point A. Can you see that, Darren? And a force that goes through the point doesn't give
That's
you
right.
a moment.
That's right. I'm sorry. It's been a while since I've had statics.
That's why we're doing this. Good question. Okay, well, I like this equation. I can solve this. In fact, I should be able to do that in my head. I'm getting 30. You guys getting 30? I'm getting 30. We just figured out this dx. It's 30. 30 kilonewtons. Now we're going to do this equation here. The sum of the forces in the x has got to be 0. Well, there's only two forces here in the x. You've got 30 going to the right, so this 30 here is going to the left. I really like my external forces in red, so I'm going to put these components in black. But what we have here is the x component is 30 kilonewtons. Isn't that nice? So now we know that, because the sum of the forces has to be 0. There's only two forces, one going to the right, one going to the left. They're both 30. And now we can get the this force dy. See what we're doing right now is we are getting the external forces on our structure. I need this dy. Okay, well, let me do that. I need to make a little room here. Now, the sum of the forces in the y, we know has to be 0. This is one of the, what do they call that? It's the equation. It's one of the equations of equilibrium. There are two conditions for equilibrium. There's that one, and there's that one. Okay, well, let's do the forces in the y. Well, in the y, we have dy, and we have ay. Now, wait a minute. I don't know what ay is, do I? Well, never mind. Never mind. Okay, I don't know what ay is. Well, let me show you this. We know this angle here. This is a 3, 4, 5 triangle. If you drew this, that would be 5 meters. It's a 3, 4, 5 triangle. And if you take the arctangent of, now it'd be the arc sine of 3 over 5, you'll get 30. I'm getting rusty now. Here, let me just do it on my calculator. What I'm doing is or you could use a tangent. Call this angle theta. That angle theta is equal to 3 over 4. It's the opposite over the hypotenuse. Now, if you do that, what you get, 3687. This angle here is 3687. Okay. So what do we know? We know dx is 30. So d cosine of 3687 is 30. And we can get d. And then we can get dy, and that'll be very helpful. Did I lose anybody on that? Gosh, this is coming out underneath the board here. I need to write this up higher, sorry. Let me write it over here. D cosine of 3687 is 30. Okay. Well, we can solve for the d then. Here goes. D would be 30 divided by that. Okay, I can do that. I'm getting 37.5 kilonewtons. we just figured out what D is. D is 37.5 kilonewtons. Now we can get dx. Here we go. No, we know dx. What I mean is dy. dy is equal to d sine of 3687. Yeah. Okay, let me do that. I'm getting dy is 22.5 kilonewtons. We think that this dy is 22. Unless I made a mistake, and if I have, I need you guys to tell me, but I think that dy is 22.5. Now we can take the sum of the forces on the whole body. Here we go. I need some room here. Sum of the forces on the whole body are dy, which is 22.5, ay, which we don't know, and minus 30 kilonewtons. There's only three forces in the vertical, we're doing the y direction here. We got 22.5 going up, ay going up, and 30 going down. So we're going to solve for ay. Well, I can almost do that in my head. Is it 7.5? Yeah. Okay, we think ay is 7.5 kilonewtons. Now, they want to know what's going on here, the internal loads at C. So we're going to do that now for them. But before I do, to do that, you have to break it into parts. See, we've been working with the whole thing. Do you have any comments or questions before we break it into parts and find out what's going on at C? Well, I wonder if we did all that right. I might have made a mistake someplace. I don't know. Now, here's one way you could check what we've done so far. You could see if the whole thing is a 3/4 member. See, you got 30 here and 7.5 here. I'll draw you a little angle here. You got, what I'm doing, I'm checking before I break it into parts. I've got 30 kilonewtons going to the left here at A. Point A. And I have 7.5 kilonewtons going up. So I can draw you that angle there. If you take the arc tangent of 7.5 over 30, I'm checking my work here. I'm making sure this is right. I hate it when I give you guys the wrong stuff. I'm getting 14 degrees. This vector at A is at 14 degrees. If I did that right. Okay. Well, let's draw it. I'm going to make a 14-degree right here. Yeah, there's my protractor. 14 degrees is right little bit messy there. Yeah, okay. 14 degrees, this puts me right about there. $14 puts me there. You see that 14 degrees? That's what we're talking about. There's 14 degrees there at A. And I don't really like it because all these are supposed to go to, are supposed to be concurrent. This angle is supposed to go, they're supposed to meet. They don't. So I must have made a mistake someplace. Let me go back over stuff here and see if I've fouled up. I think I got this angle okay. Yeah, I think that's all right. That angle's okay. Yeah, I think I drew it kind of crudely there. Yeah, that's looking a little better. See, these are all supposed to meet. Is that 14 degrees? Let me double check that. No, that's more like about 12 or 13. It's a little bit more than that. You know, I'm beginning to think we got this right, guys. It's a tad more than that. And see, these angles, these are all supposed to meet in a point. If you have a three-force structure, all the forces have to meet in a point. I should make that vector at A in red. It's more like this. There's A. And I can tell you how big it is. It's 7.5 squared. Does that show up? Not very good. How about over here? Yeah. A is 7.5 squared plus 30 squared square root. Let me try that and see what that is. 7.5 squared plus 30 squared square root. It's 30.92. 30.92 newtons. Pretty dang close, guys. Well, let's solve this and see how we did. This is how you do these problems. Now, it's possible I might have put in a wrong number someplace. That's why I need you guys to double check this stuff. But in order to find out what's happening at C, you have to take a section. So let's see if I can draw that. Do I have room here? Let's try this. This is really a hard problem. I shouldn't have picked this one. I should have picked an easier one, huh? But what we got here is, now how long is that? Well, that's 2 meters, right? So that's 4 inches on my scale. Now here's the thing, if you guys do this on get sharp pencils and have graph paper, you can get it to come out right on the money. It won't be crude like mine is, but I'm doing the best I know how. This is C right here, and this is A, And if I did that A right, that's 30.92 at 14 degrees. So I can put that on here. Let me do that. Let's see. 14 degrees. It's a little bit crude. Yeah, it's right about there, I think. And here's there's A. Now we're looking at this section here, and you have a partial distributed load here. This is 2 meters. This is 5 kilonewtons per meter. So that makes that 10. So you have 10 kilonewtons there, and A should be in red. A is 30.92 kilonewtons. I need to make this 10 much smaller. You know, 10 is smaller than 30.92. And the sum of the forces have to be 0, so I'm getting the feeling that we have to have a shear force going up. Let's see. Well, I'm not sure about that. What is the component going up? It's 7.5. So if you have 7.5, well, no, wait a minute, that's the X force. This is 7.5. What do you have in the, no, that's 30. And this is the 7.5. 7.5 going up, 30 going to the left. So when you take the sum of the forces in the Y on this section, you got 7.5 going up, 10 going down. You know what? I think you have to have 2.5. 2.5. 7.5 going up, 2.5 kilonewtons going up, minus 10 kilonewtons going down equals 0. We've just figured out the shear force. There are 4 kinds of internal loads. Let me write them for you. How are we doing on time? We're doing okay. I wonder if any of you guys know what those are. We got a wonderful class here, and you've all had statics. Let me ask one of you guys. How about Samuel? Samuel, do you remember any of the 4 different kinds of internal loads, Samuel?
The normal.
Yeah, good going, Samuel.
The normal, the shear force, and the moment.
Very good. The normal force. Samuel knows the shear force. Samuel, they call it the bending moment.
Okay.
And there's one more. Samuel, what's the last one?
I don't remember that one.
That's fine. That's fine. It's called torque. Proud of you.
Thanks.
There is no torque, so you guys can forget about torque. See, torque, I don't know, torque is when you twist, okay? There's nothing twisting any of these members, so we don't have any torque to worry about. And we just figured out the shear force. It's 2.5 kilonewtons. Now it's going up. We figured that out. And now for the normal force. Well, can you see that if you got 30 going to the left, then you have to have 30 kilonewtons going to the right. Some of the forces is 0 on this. So the normal force is 30 kilonewtons. It's tension. It's under tension. Now, we haven't done the bending moment yet, but I'm just curious. Let's look at the answer book and see how we're doing on the answers. Guys, what we have just done is problem F16. This is a fundamental problem, and the beauty is they do these for you. Isn't that nice? So we could just look back here and see how to do it. Let me see if I can find it. F16, here we go. Trying to find it. There's an answer book in the back, and it says F16. It says the normal force is 30 kilonewtons. Yay! Put a little happy face on that. We got the normal force at C. We did good. Now it says the shear force, got lost there. The shear force, now they say that the shear force is -2.5 kilonewtons. Now we got, hey, I'm going to put a happy face on that too. We got 2.5 kilonewtons. But now wait a minute. They say it's negative. Well, you need to understand something. I need a little room to show this. Let me write it over here. They made an agreement that if shear is going down on a left-hand member, it's considered positive. This is called positive shear. But see, our shear, look, our shear is going up. See it? So that's how come the answer book says the shear is negative. Yay, we got it right. Now the reason we got it right is we followed step by step. We drew the free body diagram to scale. We measured our angles. We did our equations of equilibrium. And we did not screw up. I don't think. Now, here's the final check. We're going to do the bending moment. See, we're checking our work now. Well, we haven't got the bending moment yet. Well, here's the equation. It's kind of in the bottom of the page there. I need some room. There's a bunch of room up here. Let's use this. We all know this is August the 18th of 2020. We don't need any of that jazz. We know it's problem F16. Now what we're going to do is we're going to take the sum of the moments about, but we're going to do it on our section, see? This is our little section here. There it is. And why don't we do it about this point here? That is point A. Okay. Hey, look, you see that 30.92 that has the components? That doesn't give you a moment about A. That force right there does not give you a moment about A. Let me ask somebody. I like to ask my students. I'm going to ask Noah. Noah, if you can hear me and you can unmute, I want you to tell me how come this 30.92 going through point A does not give you a moment about A. Are you with me, Noah? Who's calling Noah?
Is this in the direction of the axis?
Say that again, Noah.
Or it's in the, let's see, hold on.
This force right here, Noah, that goes through point A does not give you a moment about point A. Why is that?
because it goes through the
That's
the
it.
force.
That's it. It
Yeah, it
goes through the
force
point.
goes through the point.
It goes through the point. Let me write that down. A force that goes through, how do you spell through? There you go. A force that goes through a point gives you 0 moment about the point. I know you know that. But see, I believe in repeating stuff until it sinks in. Well, that doesn't give you any moment, but I tell you what, the 10 does. And that's going to be negative 10 kilonewtons times 1 meter. And it's negative. One of my wonderful students told me why that was negative, and I forgot who it was. Was that Shane that told me how come that this 10 kilonewtons gives you a negative moment about A? Unmute, Shane, and tell me how come this 10 kilonewtons gives you a negative moment? Why is that? He's not going to tell me. Shane, unmute. He took a coffee break. Okay, well, let's go to my friend Megan. Megan, tell me why this, what was I going to, oh yeah, why does this 10 kilonewtons give you a negative moment about point A, Megan?
Is it because it's going down?
No, that's not the answer the teacher wanted to hear, Megan.
Is it
Try
because
again. It's
the
not
clock-
because it's, huh?
because it's clockwise?
That's the answer I wanted to hear, because it's clockwise. Clockwise, remember, is negative. Okay, so we got negative. All right. And then let's see what else we got. Hey, you see that 30? That doesn't give you a moment because it goes through the point. Any force that goes through a point gives you a 0 moment. But the 2.5 does. And that's going to be a plus 2.5 kilonewtons times 2 meters. But we're not done yet. I didn't put the bending moment in there. See, here's the bending moment. We'll call that M. How's that? Now, the reason this is a plus moment is it's counterclockwise. See that 2.5 at 2 meters? That's counterclockwise. And then you have the bending moment equal to 0. And now we're going to solve this, and we're going to get our bending moment. Okay, here goes. I could almost do that in my head. I'm getting 5. I did that in my head, and I'm getting 5 kilonewton meters. If you put a 5 there, does this all add up to 0? Yeah. Okay, here's the answers, guys. We think the bending moment is 5 kilonewton meters. Let's see how we did now. We're going to go to our answer book. Go to the back and find F, whatever this was it 1.6? Is that what it was? Yeah, F1. Guys, we're doing F. If you just tuned in, we just worked on this for an hour. Fundamental problem 1.6. It's on page 16. And the answer is F1.6. F1.6. Hey, they said the answer is 5 kilonewton meters. That's what we got. We got 5 kilonewton meters. That's what the answer book says. We successfully did that problem. And I'll answer any questions now. I'm listening. Did you have any questions on that? Okay, well, I guess you don't. So what's next? Let me think here. Anybody have a comment or question?
I have a question. Could you go over which are the conventions for the internal forces, like the shear, normal, and moment, to when are they positive and when are they negative?
Thank you for asking. Now tell me your name.
Samuel?
Samuel. Thank you, Samuel. We've gone over the shear conventions, the plus and the minus for the shear. For normal, make a little room here. For normal, tension is positive, compression is negative. For shear, shear going down on the left-hand member is positive. Shear going up, as in our problem that we just did, if the shear is going up, then it's negative. Positive shear is going down on the left-hand member. Negative shear, according to the convention, really a definition, is shear is considered negative if it's going up on the left-hand member. Now, when it comes to torque, well, let's do bending moment. We've done bending moment. If you have a member like this, a left-hand member, and the bending moment is, what is that, counterclockwise? Yeah, that's counterclockwise. That's considered positive. If it's going the other way, if it's clockwise, the bending moment's clockwise. Now I forgot. Who am I talking to now?
Samuel.
Yeah, Samuel. Thank you, Samuel. If see, that almost went off the board, didn't it? Yeah, there's my finger there. If the bending moment is clockwise, it's considered negative. Now, the only other internal reaction or internal load is the torque. And let's see if I can show you that. Make a little room here someplace. We're about through here today. You know what? We've had fun. We have 5 minutes left, though. We go from 9:30 to 10:50. And you have some homework to do for me. But well, when you talk about torque, here's a member, and the torque is funny. They put a double arrow head on it, and of course, for equilibrium, you would have to have a double arrowhead in the opposite direction for equilibrium. But see, torque goes the way of a right-hand screw. If you have a right-hand screw, I don't know if you can see this. What I'm going to do is I'm going to turn this. I'm going to pretend this is a screw or a bolt, and I'm going to turn it. Now, if I turn it this way, it backs off and it moves to the right. I don't know if you guys can see that. It's going to the right. Now, if I turn it this way, it'll go the other way. It goes the way of a right-hand screw. And so this is going this way is positive. It's positive in the X direction. You always look at what's going on to the left-hand member. I shouldn't have even drawn that for you. You'll get confused. So you have to think about, if you had a screwdriver and a screw, which way, if you turn that screw, which way would it go? See, if now the book has a different way of writing it. I think they use kind of a circular deal like that. See, I prefer drawing the double arrowhead. That would be a clockwise turning, and a right-hand screw would screw in. See, that would be negative because it's in the negative X direction. Samuel, did that help any?
Yes, it did. Thanks.
Say that again.
Yes, it did. Thanks.
Oh, good. Excellent. Good. Well, we have 3 minutes, and the last thing that we're going to talk about is, I already wrote it on the board, but you're going to read your chapter, do your homework. But this whole course, where it's at is stress. And there's two kinds. There's normal stress. And the symbol for that is a little Greek letter. It's a small lowercase sigma, and it's your normal force over area. And shear stress. And it's stress that causes problems. That's the focus of this course. The symbol they use is a little Greek lowercase tau. It's a little Greek lowercase tau. This is a little Greek lowercase sigma. Now the capital sigma looks like that, and the capital tau looks like that. But shear stress is your shear force over your area. That's what we want. And what you need to know is these things are internal. Normal force, shear force, they're internal. Now later when we study, how are we doing on time? Oh, I have 2 minutes left. Later when we study the other chapters, we'll run into an equation like this. And we'll run into an equation like this. Now this is normal stress, and this is shear stress, but they're with a different kind of loading. This is with torque. See, torque is an internal loading. And we'll study this. That has a name. It's called the torsion formula. And this has a name. It's called the flexure formula. This is Bending moment. Hey, we just figured out a bending moment a little while ago. I forget what it was. Was it 5 Newton meters or kilonewton meters? 5? Or was it 25? I don't remember. But see, when you have bending, you can have normal stress. There's another equation that goes like this. This is for bending also. This is called the shear formula. We'll learn about these later, but what I'm trying to tell you now is that stress is all important in this class because stress causes problems. It causes problems with people. People can have too much stress and you can, I don't know, you can get a heart attack or a stroke. All kinds of bad things can happen if you have too much stress. Stress can break people, and stress will break structures. We don't want to design a structure that's broken because the stress was too much. That's what causes fracture. It's the stress is too much. And how do you get at stress? Well, you have to find the internal loadings. There are 4 kinds. And I forgot which wonderful student rattled them off. He forgot torque. But one of my students, he did so well, he rattled off 3 of them. There's the normal force, there's, time is up. Guys, I'm gonna have to say goodbye. It's sad. But let me find the little red button here. Here's your last chance to say anything. If you want to say anything, now's the time. I'm going to sign off. Your last chance. 5, 4, 3, 2, 1. Okay, bye-bye until I'll see you next time, okay? Bye-bye for
Mr.
now.
Griffin.
Bye-bye.